Today on Under the Big Tree, building the random source Serge modular variable slope VCF. I cut my teeth on modular synthesizers some 25 years ago at the San Francisco State University Electronic Music Studio, where I was getting my BA. There was a very early Buchla 100 there, which was great for learning on. But then there was a Serge modular that took up a whole wall. It also took up all of my time, as I was drawn to it like glue. The sound, the controls, the whole thing just resonated with me. It was the early 90s, and they ended up removing it from the studio and replacing it with a computer-based digital system that was anemic at best. The Serge ended up in the basement of a retired professor from the school that still really cared about analog. I never found out what happened after that, but I sure hope that magnificent instrument is still operational and being used by someone who appreciates its magnificence. So, you can imagine my elation when I met the folks from Random Source at Superbooth 18 and discovered that they were creating updated versions of some of Serge's greatest modules, with Serge's help himself. What's more, they were creating versions both in the original 4U Banana Jack format, but in Eurorack format as well. You can buy completed modules or take the DIY route and build them yourself. I built their new timbral oscillator at Superbooth, and we'll do a separate video on that module one of these days. But today, I want to talk about the variable slope voltage controlled filter. This module packs in a huge amount of functionality. It has simultaneous low-pass, bandpass, and high-pass outputs. It has 2 inputs and a mixer for added versatility. It has filter cutoff and resonance knobs, of course, as well as control voltage inputs for both. And it has a variable slope, which allows you to dial in the steepness of the filter on the fly. This slope works beautifully with the resonance control to allow you to dial up flavors from subtle to squelchy. There are attenuverters on both the filter cutoff and slope control voltage inputs, allowing you to reverse the polarity of the CV on the fly. And most importantly, it sounds awesome. I built 2 of them, and they have taken pride of place in my live rig. In this first of 2 episodes, we will build the DIY kit of the variable slope filter step by step. If you are not interested in building the filter, but want to hear it in action and go through the functions of the module, then go check out part 2 instead. Still here? Okay, let's heat up those soldering irons and get building. One thing to note, I purchased the kit as a panel and PCB kit only. I then sourced all the easy parts from my component pantry and purchased the rest from Mouser and Tata. I finally bought the knobs from All Electronics, my friendly local electronics store. There are bills of material with pre-built Mouser carts online along with the documentation for the build, making it really easy to place your component orders. Okay, here we are with our build for the Serge Random Source VCFS variable slope filter. I absolutely love the Random Source stuff, everything about it, the sound quality, the component quality, what it is they're trying to do. Everything about it is absolutely wonderful. And so here I am with all of the materials to try to finish up the build of these 2 filters. It was so much work that it didn't make sense to do one. I decided to do 2 at the same time. So we start our story here where I've completed all of the resistors for both of the filters. There's an awful lot of parts. It's a pretty high parts count. Definitely not a beginner's DIY project, but not impossible. There are no surface mount pieces or anything like that. However, it did take me quite a while to be able to source all of the materials. I had to go to both Mouser and Tata to be able to get all of the stuff that I needed to be able to do this build, in addition to a lot of the materials that, of course, I already had myself. So it's been a while, but I hope that the build goes smoothly and that it's going to sound as good as I think it will. We'll find out together. Okay, just another couple of thoughts here as we get started. The first one is that I use a jeweler's mask like this to be able to see. My eyes are just not good enough to be able to do quality soldering anymore. And so I use that all the time while I'm working, and it helps me be able to figure out which the correct placing is for the components and getting them in there and soldering them correctly. I use a Hakko soldering iron, and I don't use a sponge. I use this metal sponge-like material to be able to clean off the tip of the soldering iron instead. The reason being that the sponge itself, because it has water in it, lowers the temperature of the soldering iron, whereas if you just put it right into there, you're ready to go. Of course, no build can ever be complete without the two most important tools: a pair of needle nose pliers and a pair of diagonal cutters. And then, because of the fact that I'm doing it inside, I'm using this Hakko device to be able to suck all of the soldering smoke in and hopefully neutralize a lot of it through the carbon filter up on top. All right, so we've put in the first load of capacitors, the bypass caps, these little guys, and these electrolytic capacitors here. Gonna solder those up. I'm a little nervous though, because the nomenclature on the build is not the same as the nomenclature on here. So for example, on this board, these capacitors are listed as C19 and C20, but on the BOM, they're listed as C1 and C2. And so when you have that kind of thing, you have to look and make sure that you're doing it correctly as far as the detective work. So I looked over here to their drawing of what it looks like, and if I look there very closely, I can see that those are the only two electrolytic capacitors on the board, so that has to be them. One more thing that's very important, of course, these bypass caps are not polarized, but the electrolytics are. And so whenever you're putting those in, it always makes good sense to check them and make sure that you have the positive going into the positive hole and the negative going into the negative hole. Okay, I've just completed the capacitors, and you can see how many different kinds of caps there are there. They all look great. It's all done. I'm over halfway done with the actual soldering of the components onto the PCB, which is nice. Okay, so I finished soldering the 5 ICs and the power header in place. Now, they're where they need to be, but they're not all the way soldered, and I'll show you why. I have a trick that I use to get the ICs and things flat onto the board. If you look down here, you can see that I've got the two opposite diagonal points soldered. So here's one, and there's the other one right there. And the reason I do that is because I'll solder one pin down while propping the IC socket up on a pencil or something like that. And then I'll try to do the other one across the other diagonal so that it all holds in place. But then I turn around and look at it, and if either side is riding up a little bit, in other words, if it's not completely flat to the PCB, then I can use my finger to push and apply pressure to it while heating up the solder on that pin again, and then it'll push it, and then it'll go flat. And then the result of that is that all of the PCs are nice, or all of the ICs are nice and tight to the board. So now that that's done, I can go along and just finish soldering these up, and I will go in the order of going this way because I'm left-handed. So I'll do that one, and then that one, and then that one, meaning the reason being that that way the soldering iron isn't hitting other pins that are already pre-soldered, so that'll minimize the amount of solder bridges that you get. Okay, I'm done with all of the sockets, and now it's time to put the transistors in. The thing that's most important about the transistors is that they are polarity sensitive, just like electrolytic capacitors and LEDs and things like that. They have an emitter, a base, and a collector. And so what's important is that we make sure that we put the transistor in with the proper legs going to the proper ones. So I'm using 2N3NO4s, and so to make absolutely sure I'm doing it right, I went online, I took a look, double checked it, and then made a little diagram here so I know which is the emitter, which is the base, and which is the collector relative to the shape of the transistor. So that way, if I'm careful along those lines, I won't make a mistake. Okay, that's about it for the first day of our build. We've finished most of the work on the component board, which is really the hard one. I put in a couple more things after the transistors. I put in some trimmer pots right there, and then 10 ohm resistors right there to help with the power. Okay, before I put the ICs in, and particularly before I solder the expensive that 2180 VCAs into those slots, we're going to do a very important debugging step. I find that this solves so many problems that are much easier to figure out now than later on. And that is making sure that the power itself is going to the right pins on the ICs and not to the wrong pins. We start by going and getting a data sheet for the particular chips that we're using. In this case, we're using a TLO72 and an OPA 2134 op amps in this 8-pin format here, and they use the same power pins. So we only have to check one. We can see over here that pin 4 gives us our negative voltage, so we're going to be looking for negative 12 volts on pin 4, and pin 8 gives us our positive voltage, so we're going to be looking for positive 12 volts on pin 8. In the same way, as we look here at this other format for these that 2180 chips, they're just in a strip instead of in a square like this. And so pin 5 gives us our negative voltage, and pin 7 gives us our positive voltage. So with that in mind, we're going to take our little DIY Eurorack temporary power supply, and we're going to plug it in, just like we would plug in the regular Eurorack connector. So now we're getting power to this particular circuit board. And so we're going to take, we already have our device here set to looking for DC with a maximum of 20 volts. And then I'm going to just tap into the ground right there, convenient little spot right on the DIY power supply. And let's start testing out these pins. So we'll go on the top. So nothing, 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 minus 12 volts. Well, minus 14 volts. That's okay. Positive 14 volts. Nothing, nothing, and nothing. Great. So that one's good. Now we'll do the same thing here. So we don't want to see any voltage on anything other than the voltage pins. And the fact that we're getting plus and minus 14 instead of plus minus 12 is probably due to the fact that there's no load on the power supply itself. But in any case, the point is that it's showing us what we want to see. Okay, it's time to insert the ICs, and I want to share one trick that I have learned over the years. The way that the ICs come from the factory, the pins are flared out a little bit. It might be hard to see that here. But the result of that is if you take it and try to put it right into the socket, sometimes it'll work, but sometimes the pins will bend a little bit, which causes no end of frustration. So what I do before putting every IC in is I take a needle nose plier and I hold all the pins and I bend them in towards the middle just a bit, not a lot, just a little bit. And once I do that very gently, I then of course make sure that the notch is up on top. And in this case, we have a notch and we have a dot showing that pin 1 is in the upper left-hand corner, which is what we know. So we make sure that that is aligned with where the notch is on the IC socket so that we know that we are in the correct polarity. Put it in, push it in, and you're all done. Okay, that's a wrap on the component boards, except for the connector pins that will sandwich this board to this board here. Okay, so now we're moving on to the PCB that holds the pots and the audio connections, the pots and the jacks. So this is something that should be familiar to anyone who's built any of these types of Eurorack modules before. The whole process of fitting the the pots and the audio jacks. So you take the screws off, you take the bolt off, then you take these and you attach them in without soldering any of them. So it's just a pressure fit right now. I haven't soldered anything in, but they're all holding, which is great. And then we do the same thing with these Foncacon audio jacks, which are a little trickier. If you sort of drop it, they'll all fall out of place, which can be slightly annoying, but it's okay. It just makes you more careful. So we're going to put all of these on in place all at once. And the reason that we're doing this is because there are always going to be, you know, little manufacturing tolerances between the PCB and the panel. And so rather than trying to force something into place, if we leave everything a little bit loose and then attach the panel like so, very gently, then that's going to hold everything in place just right, which means that we can now solder it on the back and everything will be hunky-dory. Okay, so once I get everything on, I'm going to use just a few of these nuts, just finger tight, to hold the whole thing in place. We're going to be taking it all off again, but this just keeps this sandwich from going anywhere. Just do a couple of those. Maybe one more. All right, that's all together, and so now we can turn it over and begin soldering all of the parts on. Okay, I've successfully finished soldering all of the components to the back. For these big ground connections, I used a little bit of flux to be able to help the solder flow, because there's a lot of solder that has to go in and a lot of metal there that you have to heat up. So once we're done, we turn it over. I already magically removed the nuts, but now we can take it off. And there we have it. So we are actually almost done. All we have to do now is solder up the connections between the two boards. And the beautiful thing about these direct mount types of things is you don't have to do any wiring, which is a slow and tedious process. Oh, one other thing that's important, all of these pots are 50K except for the pot for the resonance, for the Q, which is 250K. So make sure that you put the correct pot there, otherwise sadness will ensue. Okay, so now we've completed attaching all of the jacks and knobs to these main panels. We have these component panels done. And so the last thing that we have to do is connect these two panels together. And then, of course, connect them to the panel over here. So how do we do that? Well, we're going to do it with these pin headers right here. So we've got these female headers and these male headers, and guess what? They're exactly the same width, and so we can attach them together just like that. And so what we do to attach them together is that we are going to take these connections here on these boards, and if you look, they're opposite to each other, and so we're going to create a little Eurorex sandwich, just like that. So those pins connect up to those pins across there connect up to the ones right on the other side, and these pins over here connect up to those pins. So these serve two purposes. The first one, of course, is that they're structural. So you take these and they connect up together. But the second purpose, which is really cool, is that they're also used to transmit all the signals to allow these two boards to communicate together. So these pins are holding the positions of these knobs, for example. And they will go through into here where they can then alter whatever it is that's happening in the signal flow on this board right here. So the way that we do it is that we are going to go along and cut pieces from the male and the female pin headers, just using a good old clipper to be exactly the same length here. So this one is 1, 2, 3, 4, 5, 6. So I'm just going to come up here and I'm going to count 1, 2, 3, 4, 5, 6. And then I'm going to use my little diagonal cutter to just gently bend it. I think I got 7. 1, 2, 3, 4. Which is no big deal because these are not expensive at all. And so I'll just go along and cut off the last one. And here's my 6 pins that you will see. Fits right in there like that. So what we're going to do is take this, run it through there, and solder it on top. So we put this through, and we're going to solder it here. At the same time, we will make a female one, excuse me, doing the same thing. So we've got 1, 2, 3, 4, 5, 6. I'm going to count, make sure I've got it right. 2, 3, 4. And then very gently cut it with the diagonal cutters. So now we have 1, 2, 3, 4, 5, 6, and a little bit of extra, which we will clip off. 2, 3, 4, 5, 6. There we go. So there's our 6. Now the thing is, just like attaching these things to the front panels, we're not going to solder these on separately. What we're going to do is we're going to cut all of these to fit, and then we're going to set them all up relative to each other. So we'll put the male one there in that, and then we'll put the female one here, just like that. So now we've got the male and the female, and we're going to do this with all of them before we solder them. But you can see we can now take these and make ourselves, boom, our little sandwich. So we get all of those in, so they're all connected together on both sides. And once that's done, then we solder them across. And that way any errors or any difficulties along those lines will get sorted out when we do that. Once we're done with that, then we attach the faceplate back onto the front and go in, and actually I'm going to do a little bit of cleaning up of the flux on the back of these. Once I solder these up, I'll use some rubbing alcohol to be able to clean off any flux that might be there. Okay, so before I do the soldering of the sandwich components together, I'm going to clean the main boards a little bit. Very simple. I take some isopropyl alcohol and an old toothbrush. Do not use this to brush your teeth again. Stick the toothbrush in there. Just scrubbing off all of the flux that ended up getting all over the place. And then I'm going to use these Kimtech wipes. These are not tissues. They are tissues that don't have any fibers in them that will stick to it. So they're sort of these delicate task wipers, these things that are designed for science. All done, a little bit cleaner. Okay, so now we're going to put these sandwiches together. This is a little tricky, but it requires a little bit of patience, but it's doable. So as you can see here, I have already attached the male and the female sockets in place. So I'm going to take the control side, and I'm going to put the male pins into the appropriate places, just like that. 1, 2, and 3 on the control board. Now comes the tricky part. Now we have to attach, we have to gently put the other piece on and then hold it in place as we start soldering. So this takes a little patience. It'll take a couple of times to get it right, but it's definitely doable. shaky, but I got all 3 of the sets of pins in. Now I'm going to put it down very carefully so that it sits there. And now with that in place, I can bring out the soldering iron and start to solder the pins in place very gently. There we go. So I'll do 1 on each of the tops, and then I'll turn the unit over and do 1 of each of the bottom ones, and then it will be in business. And I'll then be able to solder the rest of them at my leisure. So I'll turn this way and solder 1 pin for each of the sets. So now the overall sandwich is there, and we can just solder all of the rest of the pins, and then at that point we'll be done with all of the soldering on the module. And the build is done. Here they are with these beautiful aluminum knobs on. You know, the main reason to do this kind of work is not to save money. That's what I originally thought that DIY for Eurorack was really about. It's not. It's an artistic thing, right? Because of course it's taken me a ton of time to be able to build these things. The reason to do it is to create something yourself, and to create something that's incredibly high quality on your own, and to know that you have that much deeper of a relationship to your electronic instrument as a result of the fact that you did all the work and took all of the time to make it happen. I've got some good news and bad news. The good news is that this module is functioning properly. The bad news is that the other one is currently not. It's not passing audio. So this is actually a great opportunity to try to demonstrate how to be able to do audio troubleshooting so that we can fix it. So the materials that I have here to be able to test it are as follows. Here is the digital oscilloscope, which we have built in another video. This over here is the DIY Eurorack power supply that I've built, so I can test things away from the cabinet, which is very handy. And this is a function generator that is spitting out a square wave. So we have the function generator going into the input of the filter that's working. We have the low pass output of the filter going into the oscilloscope, and we can see that we're getting a square wave. And of course, the unit is plugged into my separate DIY power supply. So we can take a look at a couple of things here. So I'm going to start by lowering the frequency cutoff, and we can see that it's working, and that in fact, as the filter cutoff comes down, it rounds the edges of the square wave as it removes the harmonics and turns it into something more of a sine wave. Now we can bring up the resonance, and we can see as we bring it down, where is that? There it is. Now we can see the Q resonating right at the corner frequency, and that's what those jagged lines are at the edge of the square wave. So if we go very carefully, look at that, you can actually even seeing the resonance resonate. You can see that it's turning from just a single spike into into its own series of sine waves. We're seeing the actual frequency as the resonation is creating its own tone. Very, very cool. And then it goes, oh, look at that. So now it's feeding back, and then it goes a little nuts. Very interesting. So that's the resonant frequency itself. So the nice thing about the fact that we have 2 units is that we can troubleshoot the one that's not working by comparing it to the one that is working. So hopefully we can find it. I'm confident that it's probably just a bad solder joint or something like that, but we're going to go through and find out. So here is the unit that's not functioning. You can see that I have everything connected up the same way, and there's nothing coming into the oscilloscope. So we're going to take off the front panel and start tracing the input signal and see how far it goes, after first making sure that we have power going to all of the op amps as we checked previously. And the problem is solved. It took me about 10 minutes of debugging. The first thing I did was check again to make sure that I had power energizing all of the op amps, which I did. I confirmed that. And then from there, I went through and looked very carefully. And what did I discover? But a solder bridge on not one, but on two components. So once I disconnected those solder bridges, everything worked great. And just for those who don't know, a solder bridge is simply where you have two components on the PCB accidentally connected together by a clump of solder. It's really easy to happen when you've got a lot of pieces on a small circuit board, and so you need to be very, very careful with it. Fortunately, it's a fairly easy thing to debug, and as soon as I fixed it, it all worked perfectly. So now I'm going to put the plates on, I'm going to put the brand new knobs on that I went and got at the store, and then we'll take it upstairs and take a closer look on the oscilloscope and hear what these sound like. So that's how to build the random source Serge variable slope VCF. You might want to head on over to part 2 now to hear how it actually sounds.